Can everybody hear me?
Yes, we can.
All right, great. Well, welcome everybody to our next session. We're going to get started. I think Erin got everything queued up. So this week, welcome. I hope everybody enjoyed the readings and the prep for this week. So we'll be talking about that in a minute. So welcome everybody. This is our third session in the ecological economics course. And this week, our session is Economics as if Physics Mattered. Subtitle, An Introduction to Limits. So Erin and I will be going through this one, talking about more of the, you heard the social science side last time, so now you'll be hearing more of the sort of physical science side of things and how ecological economics tries to bridge sort of these two, I guess, disciplines to try to form a more complete picture of what the human behavior in the environment looks like. So as an intro to that, why don't everybody take just a couple of minutes and watch one or ideally both of these videos. They're pretty short, and you can also kind of scroll through them if you don't want to watch the whole thing. But just take a minute or two to check these out. I will try to paste the links into the chat as well. But they're pretty interesting, and they should give you a just kind of an intro to the kind of topics that we are going to be talking about in this session. So just take a few minutes to watch that, and then we'll think about what it means for what we're about to talk about. And I just pasted the links to both of the videos into the chat. So if anybody can't access them from the slide or from copying the slide, just click on the links that are in the chat window. And I'll also share my screen and play just a bit of the one video while we're watching. And as you're watching these, if anybody sort of guesses the point of what we're trying to illustrate, feel free to type it into the chat or put it into the questions. So hopefully you've seen just a little bit of these, one or both of these videos. So, oh, I see somebody typed it in. So yeah, so Rick says, it's an irreversible processes. Yes, so that's right. So these are examples of, things happening in reverse that of course in the real world don't operate in reverse. So it's extremely difficult to unscramble an egg. It requires a lot of energy, and Christmas trees tend not to burn in reverse and go back to the shape that they were in as you see them in the world. So basically, these are illustrations of a pretty fundamental principle that we keep in mind in ecological economics, and that we sort of, in some sense, criticize traditional economics as ignoring, which is entropy, which is a long-term limiting factor to economic growth. So sort of a useful but not quite precise definition of that is a measure of disorder or irreversibility in a system. And a more accurate but sort of less intuitive definition is a measure of the number of distinct ways that a thermodynamic system can be organized. So the number of different sort of configurations that you can have in a system. And the second law of thermodynamics essentially says that in a thermodynamic process, the total entropy of the total, sometimes disorder of the system involved increases with time. And a sort of useful but not quite precise way of thinking about that, if you're not experienced in this field, is that disorder in the universe increases over time. The number of states that something can be in sort of increases over time. And so I think we talked a little bit in the sort of introductory class about different sort of models of the world. And so we talked about a world where what we call an empty world, where the economy is a relatively small piece of the overall picture of what the world looks like. And then we also talked about what we call sort of a full world, where the economy takes up a large share, or almost entirely the entire share of the environment, that it essentially subsumes the entire ecosystem within it. And so both humans and nature, we use energy to create temporary order. So we use that to put things into a certain configuration, because otherwise we use it to sort of fight disorder on a temporary basis. In the end, entropy still wins, disorder still happens, because in a closed system, because the available energy essentially declines over time as we're using it. That's in a closed system where there's nothing coming in or out. And so ecological economics frames this as kind of one of its sort of basic points of consensus that all ecological economics sort of practitioners agree on, which is that the Earth is a thermodynamically closed and non-materially growing system. So the amount of stuff in it is closed and fixed, more or less. And the human economy is a subsystem of the global ecosystem. So it's that piece of that full or empty system that we saw in the previous picture of the model. And so this implies that there are limits to biophysical throughput of resources from the ecosystem through the economic subsystem and then back to the ecosystem as waste. And so that's sort of a way of articulating this thermodynamic model into an economic and ecological sort of system or model that we use. The thing is, material limits are really hard to notice when you have an empty world. So if you have a bunch of natural resources and you're consuming them, and we call that consumption a flow, if that consumption by people is very small compared to the amount of stuff, what we would call the stock, that there are in total, it's very hard to tell it's very hard to see that there are limits to the amount of stuff that you have, because your flow is very small and your stock is very big, and so it just seems like it's endless. Especially since natural systems on top of this use energy, especially energy from the sun, to renew themselves. So they are able to use energy to essentially fight entropy and to create order. Trees create themselves. They use energy to grow into complicated, ordered beings that essentially fight this process that you see in the one video where when they die or catch on fire, they become much more disordered. They become ash, basically. But when your resource use gets bigger, when the flow gets bigger in comparison to the stock, those stocks become liquidated in order to maintain the size of the flow, and so of course the stock on the other side gets smaller. Now of course it's alive, so it's regrowing to some extent, but a smaller stock also is able to renew itself at a slower rate. So like, right, you have fewer trees out there in the world. They can't grow as many new trees as they could if there were twice as many of them. So their regeneration rate also goes down as we or something else consumes them at a faster rate. One strategy that humans use to, and not just humans, but especially humans, use to combat a shrinking stock is with what we would call in economics a substitute. So something that is roughly equal in value to us, but is essentially an equivalent of something else in the economy that we care about, especially a natural resource. So, if we start running out of fish, we eat more shrimp. Or if we start running out of salmon from Alaska, we eat salmon from Canada. And for a while, at least, this works, except if the thing that we've now switched to also starts to decline and we start to run out of it too, then we either have to hopefully can switch back to the thing that we started with because maybe it's renewed itself a little bit, or we start to run out of choices. So if the total consumption is still really high in comparison to all the total available natural resources, this still becomes a problem. It still becomes a material limit in a system that essentially there isn't anything new being entered into it overall. And so, in a full world, which ecological economics argues is a closer approximation of the world we live in today than that empty world model, we start to notice this stuff. We start to run out of substitutes, or sort of the quality of the substitutes decline. So it's not a complete substitute anymore. So, you can think of if we start using up trees that have very hard wood, and then we have to substitute for a tree that has soft wood, that's not quite an equivalent of what we've substituted. So the quality is different. Or if we mine the really high density kind of ores on the planet and they get dispersed, the things that we're left with are basically either reusing the stuff that's been created and kind of dispersed over the planet, or mining for low density sort of leftover ores. And so the quality is not as good. On top of this, when we're talking about living things, living creatures form ecosystems. And so the loss of one piece of that ecosystem, of that sort of web of nature, if you want to think about it that way, can have a significant and sort of rapid reduction in other things that depend on it. So you take one creature out of the ecosystem, and lots of other creatures then are not able to survive. And so you end up losing not just the resource that you harvested, but you also potentially lose other resources that people might find value in. So this natural capital is a complement to human-made capital. So human-made capital being, physical things like buildings. Also, there's physical. So there's also human capital, which we talk about as like quality capabilities that people have that allow them to be more effective in the economy. So like labor or education. So all of these things. If we want to go back to the forest example, we've got sawmills, carpenters, schools for people to learn how to do carpentry. All of these things, because they're a complement to natural capital. When the natural capital starts to go away, the value of all those other things also declines. A sawmill isn't very valuable in just in the economic sense if there isn't much forest left. And likewise, a carpenter isn't very valuable if there isn't much wood left. And what's the point of going to carpentry school if there's no wood to build with or to make things out of? And then on top of all of that, we have pollution, and the environment has some ability to handle that pollution. But as we start to remove the natural capital, the ability of the environment to process that pollution, to make it harmless or to reduce its impact, also starts to go down, and that pollution either starts to accumulate or its severity goes up. And so that also has a negative impact on sort of the quality of both the environment and the human-made economy. And so in this full world where the size of our economy is pushing against the limits of the natural world, these things become a lot more obvious. And again, the argument is kind of that's the world that we're in today. And on top of this, the economy also provides a bunch of services that are not valued in the market. So, wood is something that actually has a dollar value, right? You can go out and buy lumber, so we have some sense of what a tree is worth in the market. But that's not its full value. There are other values that it has to us that we don't necessarily pay for. So it does other things like, say, controlling erosion or serving as a buffer for very severe storms. And those are things that we don't pay for. And in some cases, there's no substitutes for those things. So the ability of the natural world to kind of regulate the global climate, to produce oxygen, those are things that we don't currently have a human-made solution to replace them. Or in other cases, when we do have a sort of technological solution, it's often very expensive. So water purification, we can do it, right? But it's a lot cheaper when the environment does it for us. Pollination, pollinating our crops. I don't know if any of you saw a report that came out just last week highlighting the decline in sort of pollinators like bees and bats, and how many trillions of dollars they add to the global economy through services that basically we don't pay anything for. And so this is considered to be a pretty serious threat to our economy, because we don't have the money to pay for these things that nature is doing for free. And unfortunately, in sort of traditional economics, neoclassical economics, the market value of these things is basically zero. We don't have a value for them. But yet, when we lose them, we suffer. We suffer both economically as well as in other ways. All of these things that nature does for us that we don't pay for, we call them ecosystem services. And so those are all the things that nature provides to humans that are not a direct sort of market transaction. And I think Erin is now going to kind of talk about another way of kind of thinking about some of the challenges that happens when these ecosystem services are under threat or depleted. So Erin, why don't you take it away with our section on planetary boundaries.
Thanks, Kyle. So yeah, as Kyle sort of introduced, we know that we have all these ecosystem services, and we know that there is all this value that the Earth and our natural resources provide to us. But it's important for us to try and figure out, so what's the limit to how much we can use up these resources without exceeding a certain threshold where they're no longer available to us, or how much pollution we can put into our atmosphere without getting to a point where major Earth systems begin to dramatically shift or fail completely. And so the planetary boundaries reading and TED Talk that we had you watch is an attempt to do this on a global scale. So if you looked at the article, you would notice that this is an article with, dozens, if not hundreds, of authors that actually worked on this from different fields to sort of come up with these numbers, because this is really complicated and it's very difficult to figure out what is the limitation in these different categories. But it is important to do, because it's good to see numbers. We need to see where we are now, where we were pre-industrial revolution, and what's the limit to some of these boundaries. So this is broken down into several different categories, or several different Earth system processes, as they call it. And they tried to set a threshold for each one, that if you go past this threshold, you'll generate what they describe as unacceptable environmental change. And so they have a nice infographic here that breaks it down pretty easily into these different wedges. And so we have categories. I'll talk a little bit more about these categories on the next slide, but of climate change, ocean acidification, stratospheric ozone depletion, nitrogen and phosphorus cycles, global freshwater use, changing land use, biodiversity loss, atmospheric aerosol loading, and chemical pollution. And what you see here, we have this green inner circle in the middle, and this green space is considered to be the safe operating space for humanity, so we haven't exceeded this threshold. As you move out along each of these wedges, beyond the green space, that puts us into the space of a cross threshold, so an area where we'll likely see problems or have irreversible damage, like those videos we saw at the beginning of class, things that we can't undo once we get past that certain level. And with this report, they identified 3 of the major categories. You can see climate change, nitrogen cycle, and biodiversity loss, in which we've significantly already exceeded our safe zone. And so on the next slide, these are broken down, and it shows you a little bit more about what units they use to look at this. Because like I said, this is a complicated issue. You need ecologists, you need natural, scientists, geologists, economists, all different categories of people and areas of expertise to actually try and put numbers on these factors. So the three categories where we exceed are up here in red. So the first one, climate change, what they look at is CO2 concentration, so by parts per million in the atmosphere. So you've probably heard about the proposed boundary of 350 parts per million. There's a group, I think it's 360.org, actually, not 350.org, that advocates that that's the number that we can't cross. But as you can see now, we're up at 387, and this report was from 2009, so we're probably actually even past that. I have some updated data for you after this slide. And the pre-industrial value, so before the Industrial Revolution, we were at a concentration of 280 parts per million. So you can see that we've had a significant increase there. We're beyond what they consider to be the proposed boundary, so at which point climate change will inevitably occur. And so they also look at radiative forcing, which is how much of Earth's sunlight is trapped here at Earth as heat versus reflected back into the atmosphere. And as you can see, that's increased significantly as well. So biodiversity loss, they're looking at extinction rate, so species per million species per year. Again, very low pre-industrial values, a current rate of over 100 per million species going extinct each year, which is over 10 times where that level should be. So the nitrogen cycles, another big one. The main use of nitrogen is in chemical fertilizers. So we take nitrogen out of the atmosphere and make it into fertilizers, which can be applied to our crops. One of the main problems with that is a lot of that nitrogen ends up polluting waterways through agricultural runoff. So again, you can see a big difference here. Pre-industrial value of 0. We weren't taking any nitrogen out of the atmosphere for human use. Proposed boundary of 35, and we're currently at a level of 121. So phosphorus cycle, again, like nitrogen, phosphorus is an agricultural product. It's mined from the earth, and it's put onto crops to replace nutrients that are lost when crops are harvested. And it also has the problem that it ends up in our oceans. Stratospheric ozone depletion is actually a good example of where we've done a pretty decent job at not exceeding our limits and putting into place good regulations that prevent this type of pollution from occurring, things like banning aerosol sprays. So we're in the safe operating status. We've still depleted more than we had in the pre-industrial era, but we're not yet at that boundary. So ocean acidification. So again, we're in the safe operating space there, but we're below the pre-industrial value and somewhat close to the proposed boundary. Freshwater use is how much water humans are using each year. And again here, we're within the safe operating space, but you can see we have significant increase from the pre-industrial value, so that's a place where we could potentially, with population growth and increasing use of freshwater, for crops and other uses, could fall into that sort of danger zone. Land use change is measured in % of global land cover that's been converted from forest or whatever it was previously into crop land. Atmospheric aerosol loading and chemical pollution are two that are complicated because they're complicated and they both involve a number of different types of pollutants. They don't yet have they're not able to determine what actually this number is. You can't just put one number on, how many of these different chemicals and plastics and heavy metals are polluted into the atmosphere. It's also very difficult to determine what actually is a boundary, a safe operating space for these types of things. And because of that, you notice on the first slide that these two categories were left blank. They weren't really filled in yet. So they also don't really have a good measurement of what the pre-industrial value is. So as time goes on, these are the types of things that climate scientists are working and ecologists are working to help determine, but we don't quite have those numbers yet. All right, and so like I said, there's lots of different disciplines working on, oops, sorry, Kyle, can you go back one for a second? lots of different disciplines working on this, and there's three main branches of inquiry that people working on planetary boundaries and on this specific project are trying to figure out. So the first is that they're trying to address the scale of human action in relation to the capacity of Earth to sustain it. So how much are humans actually contributing to these different categories versus how much is the Earth actually able to withstand? And that's one of the major things that ecological economics looks at. So they're also working on understanding the essential Earth processes. So like I said, these things are complicated. Understanding how the nitrogen cycle works is complicated in and of itself, not to mention trying to figure out what are the limits and how much humans are contributing to it. And so they're also doing research into resilience. So resilience means how well a system is able to bounce back from some sort of external force or shock. And they're looking at the links between different systems. And so all of these things are related, obviously. Nitrogen and phosphorus runoff can contribute to ocean acidification and water contamination. So they're kind of looking at links between the different categories themselves, and how does biodiversity loss relate to some of these other systems as well. Okay, go ahead. So we had you read the 2009 article and watch the TED Talk because the 2009 article gives a better general overview of what they're looking to do and what these different boundaries are, and what the research involves. But they have an updated paper or some updated data, and there are slight differences between then and now. So they broke down, before we had biodiversity loss as the one main category, so up to your top left, and they broke that down into biosphere integrity and divided into genetic diversity, so diversity of species or biodiversity loss, and functional diversity, so what the role of those species is, and are there some species that do the same thing, so if we lose one, it wouldn't be such a problem if we still maintain the other. Again, because that's a complicated category as well, they haven't yet quantified that. And what they were calling, I think before was called chemical pollution, they're now calling novel entities, and those are things like those heavy metals and new types of pollutants that are being introduced into the atmosphere and into nature. So, but you can see the other things look pretty similar. They've also sort of changed the way they do it. Instead of just having a green zone and a red zone, they sort of have a red, yellow, and green. So you can see this blue circle in the center. That's the safe operating zone, those green zones there. And now you have this outer red circle. So in between the blue and the red, the categories that look like they're yellow or orange, that's kind of called the zone of uncertainty. Because it's not quite a cutoff. You don't hit a certain point and then all of a sudden things, come crashing down and are irreversible. We have a bit of uncertainty in knowing where that point actually is. So it makes sense to actually have a zone of uncertainty in between those two. It's not quite a clear-cut boundary. So those are the major changes, adding a zone of uncertainty and sort of changing the names of some of those categories, but the results look pretty similar. It's the same categories where they see the problems, although before climate change was in the red zone, now they've kind of quantified climate change as being in the yellow zone, not quite in the red zone. And if you're interested in reading the updated data, we can send you the links for this. And in addition to putting the updated data into that same type of graph, they've also broken it down and showed you some of the individual categories, those individual thresholds by region, which is important because not all categories will impact all regions equally, and not at the same time, not all regions are equally contributing to the problems of all categories. So things like phosphorus and nitrogen use, like I mentioned, those are primarily agricultural products, so you'd expect to see those in areas that have a high level of intensified agriculture. So you see parts of the United States, Europe, China, and Southeast Asia are all beyond the zone of uncertainty because they're already using such high levels of phosphorus and nitrogen on their soils. Land system change, we talked about that one, is where they look at it as a percentage of land that's been converted to agricultural land. So you see some problems here in sub-Saharan Africa. So specifically this region is the tropical rainforest region, where forests are being cut down and used for cropland at a pretty quick rate. A lot of it's not even being changed by African countries themselves. China and other industrializing nations are buying up tracts of land in in Africa, and using them to grow agricultural products that they're then exporting back to their own countries. And Southeast Asia is having similar issues with lots of forests being converted into agricultural lands. So fresh water use in the bottom right, you can see here India, parts of Europe, and the southern United States, California, and Mexico are areas where we've exceeded the safe operating space for drinking water availability. These are regions where you typically hear about water scarcity and issues of drought, so it isn't a surprise to see that these are the areas that are above the safe operating boundary. So this graph is important because it shows where these different categories occur. Like I mentioned, not all limits are exceeded equally in all regions of the world. So it's helpful to be able to break them down and look at them on a regional basis. And with that, I think we're jumping back to you, Kyle.
Thanks. Thanks, Erin. So another way of trying to conceptualize our natural resource use, especially in comparison to what might be sort of safe operating limits, is a technique or methodology called the ecological footprint. And so it's basically another way of trying to view this same idea. And so this approach, it looks at the idea of sort of how much sort of natural resources there are in the world, and that's what's sort of called in the system biocapacity, so the capacity of nature to provide resources, taking into account the sort of new production that it creates every year, as well as the stuff that's already there, in comparison to the consumption that people have of those resources. And so it's sort of broken down into a couple of different areas, which is basically carbon footprint, sort of built up land, land that's been converted to sort of non-productive use, so cities and that kind of stuff, forestry land, croplands and pastures, and sort of fisheries. And so that's kind of the stuff that nature provides, and then there's this question of, that's kind of our footprint on that land and how we use it. And so if you look at sort of a global trend based on this system, what you see is that, again, at least globally, starting in about the late 60s, early 70s, our sort of consumption began to exceed what nature is providing. And so essentially these are the flows we talked about at the beginning. So like our flow of stuff, of consumption, now exceeds what the planet is regenerating. And so what that means is that the stock of stuff, of natural resources that's available, at least the natural resources that this measures, are now declining. And so we're on a trend to run out of some of the stuff that we need. So some of those ecosystem services are becoming degraded, and some of the natural resources that we depend on, the living natural resources, are in decline, right? And so that sort of relates to what Erin was saying, but it's a different way of conceptualizing it. Not without its critiques, of course. All of these things are not perfect models of the world. They have gaps and limitations. But the interesting thing is that sort of no matter which way of conceptualizing our natural resource use that we use, whether it's planetary boundaries, whether it's ecological footprint, whether it's just sort of basic accounting of resources, the same message comes across no matter the technique, which is that our current rate of consumption is exceeding the stuff that's available, and we're running into a situation where we seem to be running out of, we may be running out of some of the things that we value. And this is interesting because these are pretty significant limits just for the economic well-being of people. So even if we just look at the dollar value in the market of the stuff that we care about, these are significant. If we add other types of value on top of dollar value, on top of economic value, these become even more significant. So we know that people get value out of the natural world beyond, what they pay, right? You get value from seeing a sunset or seeing a beautiful scenery, and that's the value that means something to you, but that isn't a dollar value. You're not going to pay. You don't have any. It's hard to quantify that number, and yet it's there. You know that you get more value out of seeing certain things in the natural world than others, and that they're not zero. And so economists and ecological economics practitioners have gotten as far as kind of giving names to these things and recognizing that they exist, but we've had difficulty in figuring out what those values are and quantifying them, and in some cases trying to translate them into an economic value or a dollar value, because they kind of defy our traditional economic system. They go beyond the way that we think of value. So some of the values that we've been able to kind of define are what we call existence value. So it's literally just the value that you have of knowing that something in the world exists. Whether you see it or not, it means something to you. So the fact that, for some people, let's say whales exist, it means something to them. But even if you never see one, you still care that they're out there. And people have this value. Not everybody has it, and not everybody has it for all the same things, but collectively we as people have this value. And so this existence value means something, right? Just the fact that it's there is valuable. And on top of that, we have a value for some people of being able to see some of these things. So being able to go to the Grand Canyon and see the Grand Canyon is valuable to you. It's significant, at least for some people. And that value is on top of the value that you have just knowing that the Grand Canyon exists, period. And then there's another value. So that's what we sort of call use value. And then there's another value, which is the value that we assign to knowing that we'll be able to pass something on to future generations. So it's not just knowing that we can enjoy it or knowing that it exists today, but actually this idea that we value having something be available for others in the future. This is what we often call the quest value. So it's like if you give somebody like something in your will, you're like gifting it to them. It's kind of the same idea. Like you have a value in knowing that they'll be able to enjoy it in the future, not even today. And all of these things are important. And if we add these values onto just the economic value of these natural systems that are in decline, the total sort of worth that they hold is even larger. We can't put a dollar value on it, but we know that it's big, and we know that it's bigger than just the dollar value. And then on top of that, if we think that these living creatures have value in and of themselves, that is, that they have some sort of right to be alive or some existence value that is totally separate from sort of the human value that we assign them, as if to say that they have value in and of themselves, in the same way that, like, I as a person have value in being alive and being myself, even if nobody else cares about me. I still assign value to myself, even if nobody else does. If we think that, or if we recognize that these living things have value of their own that is separate from human value, then that's just another sort of value that's stacked onto the non-economic human value and the economic human value that these things have. And essentially, when you pile on all those different kinds of value, the sort of worth of these natural systems is even larger, and the potential loss, if they continue to be in decline like we see that they are today, becomes even greater. So it just essentially compounds the severity of the challenges that we face. Not to be, negative, it's good for us, and it's a contribution of ecological economics that we are recognizing that these values exist. Because whether we recognize them or not, they are potentially there. And so it's important that we understand that they are there, because that helps us to make better decisions and to assess, the real sort of potential loss if we lose them. So that's pretty, that's a big deal. And those are kind of some of the bigger contributions that ecological economics has made to our understanding of a sort of more full values system to the world, and also to some of the techniques that are being used to help understand what those values are. Not to say that planetary boundaries is just an ecological economics tool, or that ecological footprint is just an ecological economics tool. Other disciplines have contributed to these ideas too, but ecological economics has been one of the important ones. And so next week we'll kind of build on this conceptualization of the world and say, okay, now that we've built this model and we've built this system of the world, this thermodynamically closed system where the human economy is part of this bigger global ecosystem, and where these biophysical limits have an impact, and as we talked about last week, where human behavior often leads us astray in the way that we manage those resources, the question then becomes, what do we do about it? And so the second part of this ecological economics sort of core concept is that ecological economics practitioners recognize that we need to kind of develop, as they say it, a future vision of a sustainable planet that has high quality of life for all of its citizens, so both humans and other species, and that we achieve that high quality of life within the material limits that are imposed by item number one, by sort of consensus point number one. So the question now becomes, you know it, so what do we do about it? That is a topic for next time. And so for next week, some of the things we will be looking at are a very sort of seminal paper by some ecological economics practitioners that is try to actually put some dollar value on some of these ecosystem services and natural capital, and actually try to understand what the size of the stuff that nature contributes to us is worth in dollar value, at least, in comparison to sort of the size of the economy that we have built out of that stuff. And then also sort of there's an interview with this one of these same authors, Rob Costanza, that sort of he tries to explain what ecological economics is and what tools we use and how we conceptualize the world. So that's some stuff for next time for you to look at. Those should be in the course folder for you to look at. And then one of the things that we want to do, just as a way of closing out and trying to think about these things for this week, is to think about these two discussion questions. And I'll give you some a Google slide to look at for us to write those answers down. But the questions are, can you think of any other limits to economic growth that we haven't talked about in this lecture? The point is that there are some, but we want to get you to try to think about what those might be. So what are some other limitations to economic growth beyond just these very large material limits? And then the other question is, on the other hand, can you think of any loopholes to the biophysical limits of the planet? Is there anything that might be a way of escaping this, these sets of material or planetary limits that are out there? So what I'm going to do now, I see there's one question, and I'll jump to that in a minute. What I'll do now is share a slide with you all that you can edit, you can contribute to, that has some of these questions. So feel free to just type into this slide that I'm putting in the chat right now. I think it was linked also. And so feel free to jump on this slide and fill in your own thoughts about either of these questions. And I will jump to the question now.
And if people also want to talk and speak about it, instead of typing, if that's easier, if you just click the raise hand,
yep,
we can give you speaking privileges too. So we'd love to get
yep, either way.
the discussion going.
So thinking about question one, are there any other limits to economic growth that we didn't talk about? These could be, smaller limitations, things that are beyond just the economy, but also are sort of less than, the massive material limits to sort of the flow of material that comes in. I see one coming up. And so, yeah, so there's a good one here that is being mentioned, which is the sort of legal limits in which the economy operates, which is definitely true. That's certainly one that sort of gets into sort of the realm of political economy and the impact that sort of decisions made by different groups of people with different goals and powers can have, and how they can conflict with each other. And so legal structure, how an economy is organized, how a group of decision makers is organized, that matters for sure, and can put limits on economic growth for sure. So that's a good one. It's not necessarily a biophysical limit, but it is very, very real, and it's one that we have made more progress in incorporating into our decision making than biophysical limits, but one that we still are still challenged by. Yeah, migration of movements of people, so localized environmental failures. That's definitely true. Not all materials in the environment just flow from one place to another. So as you saw in kind of Erin's slides on localized planetary boundaries, these are issues that you can run out of stuff in one area before you run out of it in another, and also people and animals can move, and so that also can put dynamic sort of changes on more localized environments and cause you to, it creates limits within the internal system, right? And that can matter a lot because, as we said before, there are sort of connections between different parts of the ecosystem, and also connections, of course, between different groups of people in civilization. And so having a catastrophic loss in one area can have ripple effects on other areas, even if there's more resources available in one part of the world than another. I think last year when we did this course, someone mentioned a similar idea, which is sort of that you can have resource conflicts, right? That you can have people fighting over a localized depletion of resources, and that conflict can create things like war or other sort of conflict, and that those then can have an impact. They put limits on the economy, right? Because when you're busy fighting each other, it's harder to run a stable, organized economy. And so essentially, even if you don't run out of stuff, if you get close enough to running out of stuff that you start fighting with each other, that's essentially a limit on the economy, because if it's too disruptive, if it's too much fighting, it's still a limit on the sort of economic growth that you can have, even if you have some resources left over. So yeah, those are great examples. Continue to put more of those examples into this slide, but I will just briefly jump over to the other slide just so we can talk about some of these as well. So loopholes in biophysical limits of the planet. Yeah, so space is a loophole in the biophysical limit. It's not a very real loophole today, but potentially with technological improvement, it could be, right? So on the one hand, on a very, very minor, tiny little level, it's always been true, because over time, as sort of the planet moves through the universe, it accumulates a little bit of material from outside in space. So a little bit of material falls onto the planet, in addition to the energy from the sun, and this material adds to the material limits material stocks that are available. It's very tiny, very, very tiny in comparison to what's available, but it is a tiny little loophole. And then there's a much bigger loophole that could be, which is like we go out there and we get stuff, right? So we mine asteroids for natural resources that are not available here. Maybe not living resources, but fundamental elements and things like that. And that's big. That could be something that would allow us to exceed the limits of the planet. Now, if you then extend thermodynamics, which the universe already does this, to going beyond the planet, it doesn't change. It's just that we start to define, the universe as our closed system rather than the planet. Those material limits then become much smaller compared to the amount that we use today, but they also don't fundamentally change how we operate. And so the challenge also is, even if we can achieve some of these things, if we can start getting materials from space, can we do it before the impact from exceeding the limits that we face on the planet get so big that they start to fundamentally hurt or destroy our civilization at a level that it makes it difficult for us to exceed those things. So it becomes, as some ecological economics practitioners talk about it, a bottleneck. That we're in this, that this sort of century is potentially a bottleneck where our capability to address these challenges is being squeezed by the challenges themselves, and we don't know which of those two competing forces, sort of our own ingenuity of getting out of the problem, not just technological ingenuity, but sort of political systems, awareness of the problem, ways that our society operates, whether those things will win out before the squeeze of the loss of biodiversity, climate change, all of those other boundaries start to squeeze us too much. And so that's one way. And then, of course, yeah, so people are bringing up geoengineering, which, of course, is a way, potentially, of dealing with some of these challenges. Geoengineering, in some sense, you can think about is basically replacing ecosystem services with technology. So it's a way of sort of resetting the clock or putting in place a system that replicates something that an ecosystem service currently provides. The challenge, of course, is that, one, we don't have systems yet in terms of geoengineering that can fully replicate what nature provides. The second challenge is that they're expensive currently in many cases, and then the third challenge, of course, is potentially unintended consequences. But yeah, geoengineering is certainly one potential way of exceeding these loopholes, at least in the short term. Maybe not infinitely, but yeah, good one. Solar input seems to be a relatively unlimited resource. Right, someone said, yeah, it's not really unlimited, but at least in comparison to the size of our economy right now, it is very large. And of course, that is just a way of fighting entropy in the short term, right? Eventually, the energy that we put in still gets disorganized, and the system doesn't. We don't lose it, but it is one way of. It's the biggest thing that we use to fight entropy today. The challenge, of course, is that it's not infinite. We don't make perfect use of it, and eventually it does run out. And also, if our economy continues to get bigger and bigger and bigger, there is potentially a point where the size of the economy is the same size as the energy coming into the planet. And then we have another challenge. It's not today's challenge, but it's tomorrow's challenge. And there was a question here, are there any studies going on to try to put a value on things like existence value, viewing value, et cetera? And yeah, there definitely are. Gabrielle, that's a great question. There's actually quite a lot of work in both ecological economics and environmental economics that people are trying to figure out or trying to assign at least a partial economic value to some of these other concepts. So trying to see what value in the economy people might assign to something like knowing that something exists. So for example, like a really weak example of this, but sort of in the right direction is like donations to charity. So like people donate money to preserving natural resources. Even if you never see those resources, right? Even if you give money to save the whales, but you never see a whale yourself, that's some indication of at least a piece of your sort of existence value for whales, or maybe even your bequest value, because you want to make sure that your grandkids will be able to see whales. And so you're giving money today to make sure that they happen. So there's a lot of research in this area. It's a big, big topic.
And we'll talk a little bit about that next week too. We're going to talk about valuation of ecosystem services and how we can value things like cultural and spiritual use. And I think as like engineers and economists, it's sometimes our desire to be like, okay, well, let's put a dollar value on cultural or spiritual use. But part of what ecological economics says is we don't have to put that dollar value there. When you present the value of a forest, you can present it as, $100,000 of monetary value plus the spiritual value of this certain tribe or group that uses the forest and the cultural value of people enjoying it. So we don't necessarily have to put a number on those things. We just have to show that they're there and real. And obviously it's nice to put numbers on things because then you can make easy comparisons and compare, having the forest to not having the forest. But for certain things you can't really do that. You can't put that value into numerical terms.
Yep, and I would say that's actually one of the sort of fundamental differences or approaches to the ecological economics and related fields offer that other sort of environmentally focused economic fields do not. So it feels like environmental economics is trying to put a dollar value on everything in the natural world, whereas ecological economics is trying to both do that to some extent, but also say, okay, how can we make decisions given that we know these things have value, but also given that we know some of that value cannot be expressed in economic terms. How do we incorporate those values into our decision making in other ways instead of just trying to put it all into a spreadsheet? So some other ones. So looking at the first slide again, somebody mentioned ethical limits as a limitation on economic growth, and so that's absolutely true, right? Like even in a sort of very sort of libertarian version of a free market where you know anybody can sort of buy and sell whatever they want, and anybody is free to engage in any economic activity that they want. The reality is that even in a market that most economists would describe as a free market, there actually are limits on what economic transactions people undertake. So like most people, even in a totally sort of unregulated economic activity market, don't go out and like kill their competitors, right? Like you might try to beat them, you might try to kill them on the price of your product versus somebody else's product, but you don't literally go out and murder them, right? Because that's an ethical limit that people impose on themselves and on each other that does have the impact of essentially limiting economic activity. We think that that's worth it, right? That's like a value that we hold that is not a dollar value, and it does impose a limit. And so it's important to understand that those limitations exist in some sense, right? So that's a great example. Other examples on loopholes were, yeah, we could send all of our waste into outer space, right? So just export our pollution somewhere else, and then bring back stuff from asteroids or some other planet. So that becomes essentially extending the model to other planets where they absorb the waste and they give us resources, and we don't have to worry about them on our planet. Yep, all those things are true, right? Right, another biophysical limit in some sense is like if we really screw this up and sort of our pollution or whatever overwhelms us, that would essentially shrink the size of the economy because it would shrink the number of people who are involved in it, which is not a good way out of the system. That's exactly the kind of scenario that ecological economics is trying to avoid happening, but it is certainly true that is not exactly a loophole. It's more of a consequence of exceeding our limits, right? So all of these are challenges. So these are good, very good examples from folks on both of these points. So we are at the top of the hour, so I want to thank everybody for staying. We'll stay a couple more minutes, but you're welcome to head out now. So thanks again for joining us this week. And like I said, and like Erin said, next week we're going to transition into the tools that ecological economics practitioners use to try to address both the social and the biophysical challenges that we have as a society operating within these potential limits. And there's a lot of tools, so you'll get to see how ecological economics folks are really making use of this sort of new discipline and these new sets of tools to address these challenges. So if today was a little bit depressing, next week I think we'll be a little more hopeful because we'll get to see all the progress that we've made in addressing these things. So thanks a lot. Have a great day, and we will talk to you all next week. Looking at the last slide, yep, bringing back lost species, Jurassic Park style.
That was mine.
Which is, that's right, but it's a potential, right? It's a way of, it's just like the earlier example of, sending our garbage into space. It's a, it's a technological solution to a challenge. We killed off all these species. Turns out that was a bad idea, so let's bring them back. And so, yeah, I mean, that's a potential way of addressing one of those limitations, right? Is essentially using our energy and our sort of human capital to restore something that we create, a piece of disorder that we created in the world.
And
yeah,
obviously with things like that and things like moving to space or sending our trash to space, you can see that, the cost to society of doing it on our own and replacing an ecosystem service is extremely greater than the cost of just letting nature do it by itself, which is essentially free. The science and technology and time that would go back into bringing, even a tiny plant species back is extremely a limiting factor to that being a viable option.
Right. And it goes back essentially to our second lesson, right, which is that the cost is so much greater, but we as people have difficulty both thinking about the things that don't yet exist. So, like, it's hard for us to conceptualize how much it would take to restore something until it's already gone. So we have trouble both thinking into the future very far and also fully balancing, right? We're not like fully rational beings who can just do all of the accounting in our heads and figure out all the costs and benefits of every decision. We sometimes make the decisions that are easiest or immediate first, and then it's like, oh crap, we probably have now put ourselves in a position where we either permanently lost something or we're going to have to spend a lot of money to bring it back and a lot of time. And so figuring out how to make the better decision up front before we have to spend so much money to restore an ecosystem service is one of the challenges, one of the principal challenges of ecological economics and behavioral economics and all of those sort of fields. Sure. It's because I use it. This is a question for me about the language settings. It's because I use them for work, and so it's a way of helping me build my technical vocabulary or reinforce my technical vocabulary. Yeah, cool.
I like the other one on here that essentially sounds like the plot to some sort of sci-fi movie where we make a immortal super species.
Right.
And it's funny because some of them do, like, these are movie things. Jurassic Park is a movie. WALL-E is a movie. These are, like, concepts that are kind of ridiculous, but at the same time, we have to be like, maybe that is a possibility that we'd have to look into if we get beyond a certain point. A little scary.
Right. Right. Yeah, and also it's an interesting tool, right? Because people, it's a social tool because people are captivated by arts and culture. It's a way of communicating ideas to large groups of people that are otherwise difficult to communicate, right? So it's easy. It's hard to write a scientific paper in which you talk about, mining asteroids and the economic calculations of doing that and getting a large number of people to read that and really internalize and go, yeah, that's what we should do. But you can make a movie about it and people get sucked into that concept very easily. So there is a certain, there's something to be learned there, right? That it's a way that we can sort of get around some of the challenges of our sort of limited brain and bring people on board to ideas and ways of sort of organizing ourselves in society that we might not otherwise be able to convince people of. So learning how to make good use of things like movies, television, culture, the arts as tools for our communication of these concepts is really important, right? Like the planetary boundaries is basically a communications tool. It's a way of taking information that we already knew in different settings and turning it into a nice, easy visualization that people can pick up on quickly and easily.
Yeah,
and it's been very effective. Like people get it.
And that speaks to some of the behavioral economics concepts we talked about last week with, availability and what people see and the way people react. People have a hard time, like you said, digesting a complex topic like that, but they can easily focus on, one certain character or one certain species. And there's a lot of info out there about why we choose to focus on polar bears when we talk about climate change. Really, it's people that are going to be impacted, but the impacts are so complex and affect so many species that we can just, take this cute, fuzzy spokes animal and promote saving the polar bears, and people see it and think it's cute and think it's important, and they can process that, and people are more likely to react to a single individual, like I talked about in the example last week with like cancer fundraising or single species into such a major problem like this.
Right, right. Yeah, exactly. Or why, why is an infographic like a planetary boundary so effective? Because, we are very, very visual beings, right? We've been processing information visually for a lot longer than we've been reading stuff. So it's a lot easier to communicate things graphically and through our eyes than it is to try to get us to read something and interpret it through language, because language is even though we're good at it, it's something that we have been doing for, in some respects, a lot less time. Right?
Evolutionary psychology.
Exactly. Let's make use of the fact that we've spent millions of years, trying to look out for the lions in the savannah, and a lot less time writing books. Whatever it takes for us to communicate ideas effectively, let's do it. Okay, I'm going to end the presentation, but
stop recording. And for anyone who's still here, we'll talk to you next week, and feel free to email with questions.